So we know for polynomial degree 3, there are only two types of graphs. Okay, so if y equals ax cubed plus bx squared plus cx plus d, right? Then the graph will be only these two types. Another type will be like that. It's like a parabola, quadratic function. We know that parabola, open upward or downward, right? And this is two typical graphs. So for polynomial degree 3, you are going to have one local maximum value, one local minimum value. If it's defined the whole line, you don't have absolute maximum, don't have absolute minimum value. Okay. All right. So now, if you are given an equation such like x cubed, okay, minus like 10x, right, plus, I just give an example, random example, right? And what do you have? You can sketch the graph. I'm going to change it to 16 because I really want to get integers. So you can sketch. You can find the local maximum value, local minimum value, and where you're going to get a local maximum value and local minimum value. Okay, so the leading coefficient here is 1. So I know the graph must look like that. Okay, and also when I see x equals 0, the y value is going to be 0. So it's passing through the origin. Okay, I'm going to determine 2 points here, and x cubed minus 16x equals 0. You get x squared minus 16 times x. So another 2x intercept will be x squared equals 16, right? So that means x equals plus minus 4. So you have a 4 point. So clearly the graph looks like that. Wait a minute, I'm trying the wrong picture. All right. All right, so that is graph. So this graph tells you are going to have two critical numbers, right? Two critical numbers. Right. So just find the derivative. 3x squared minus 16, set this to be 0. Then x squared equals 16 over 3. X is going to be plus minus square root of 16 over 3. So it is going to be some number, 4 divided by square root of 3. Somewhere here, it's a symmetric. When it's here as when it's here. So what is the maximum value of the function? Right? The local maximum value is going to be the value of the function when x is going to negative. Okay, you can simplify this. And then the local minimum value is going to be the value function at this point. Okay. Well, you can simplify. It's clear from the picture, right? When x equals 4 square root of 3, it's a positive number, then the function is a local minimum value. So we solve the problem. The question is, what is the local maximum value, local minimum value of the function? And it's polynomial degree 3, so this yeah, you can easily find out. Okay, you know how does the graph look like. Okay. Well, for a function polynomial degree 4. Okay. it is hard to schedule graph, but we want to check whether the function has a solution, whether this equation has a solution. Does this have a solution or not? Does it have a solution? And where can you do estimate? Okay. The graph of a polynomial degree 4 where it looks like that. Okay. The leading coefficient is positive, it's open upward. It looks like a parabola, but we twist it in the middle. Okay. Twist it in the middle. Because if you ignore the rest of parts, if you ignore the rest part, then extra force is going to parabola. Now you get some voice. If you look at this, I'm not sure I'm going to have a, there's a possibility it's above the x-axis. If it's above the x-axis, it have no solution. It's not like polynomial degree 3, one end is if positive infinity, the other end is negative infinity. So it must pass through the x-axis. But there is a possibility, no solution. So I'm going to look at this equation, right? To prove whether the function has a equation has a solution, you just need to check whether the function has the opposite sign. Okay? Then you use an intermediate variance theorem to prove there is a solution in some interval. And my question is, does it have a solution? Right? So let's check. F of 0 is going to be 1, right? And f of positive 1, it's going to be 1 plus 1. It's going to be actually is 5. It's large. So how about negative 1? Negative 1 to the fourth power, 3 to the negative 1 plus 1. And 1 plus 1 minus 3 is negative 1. Okay, it's negative. Great. It has the opposite sign. So therefore, by the intermediate variance theorem, okay, there is a solution in the interval between negative and 0. Okay, that. Okay, it's possible you're going to have two solutions for polynomial degree 4. Okay, if the axis across this graph at 4 places, then you get 4 solutions. But maybe there's only one. If there's one solution, you should get 2 solutions, unless it's touched, right? Because of graph, behavior of the graph, I should have another solution. Okay. Yeah. So up must be down, right? You cannot have just only one single solution because of this polynomial degree 4. Okay. Let's try and let's draw the graph. When x equals 0, that's 1, right? It's passing through this. When x equals negative 1, it's negative, so it's going through that. So I'm pretty sure it does still have to go up. Okay, it's go up. Okay, and maybe the other place it maybe looks like that. It's possible, no others. Yeah, you only got 2 x-intercepts. It's possible. So let's try f negative 2. F negative 2 is negative 2 to the fourth power plus 3 times negative 2 plus 1. So a negative 2 to the fourth power is 16. 16 minus 6 plus 1, it is going to be 11. It's positive. So f negative 2 is negative 2 and 11. It's positive. So somewhere here, okay. So there is a solution in the interval from negative 2 and negative 1 also. So you get a pair of loops. So this is very useful theorem to check whether the function has absolute has a solution somehow. Okay, now we almost sketched the graph actually, right? But I don't know where's the local maximum value, where's the local minimum value. You have to find the second. You have to find the critical numbers. Okay, but it's easy to find the critical numbers for this particular function. But we're not going to do that. We just want to look at whether the function has this equation has a solution or not. As we call roots. Okay. All right. So now let's take a look at the next problem. We want to study this function, square root x. Okay. And this is will be any number. Okay, I just put a here, minus x. A is a positive number. Okay, I can choose a specific number later on, because this is a typical function. First of all, yeah, the domain of this function is going to be all the x greater than or equal to 0, right? So the function is only the graph. And when x equals 0, f of 0 is going to be 0, right? So it's clear the graph passing through this, starting from this point. But we also know that when x equals a, f of a is also 0. So that's a. For x between 0 and a, it's positive. So the graph looks like that. Okay. So you immediately can see the graph. Yeah, when x between 0 and a, the function is positive. So the graph is above the x-axis. When x is greater than a minus x is negative. So that's why it's below the axis. Okay. How do we sketch the graph? So we already know the graph, right? Yeah, this is a graph. But I do need to know the concavity. Whether it looks like the second derivative is always negative, right? Concave down. But there's a possibility somewhere concave up when x sufficient large. Could be like that, go concave up, right? I don't know. So we have to find we have to find this point first, right? This is a critical number. Give it, yeah, f of x is going to be 8 times x to the 1/2, x to the 3/2. So the derivative is 8 times 1/2, x to the negative 1/2, minus 3/2, x to the 1/2. And you have to solve this. All right? You have to solve this. And how do I solve it? I multiply both sides by x to the 1/2. And then I get half of a minus 3/2, and x equals 0. So this is a very simple equation. X equals a over 3. Okay, x equals a over 3. A over 3. So that is a critical number. Okay, then the f of a over 3 is going to be the local. Is going to be local maximum value. I don't know. Always happen here in this class. Never happened in my another class. Okay. So so the local maximum value is going to be the value of the function at a over 3. Okay. Yeah. Okay. So you have to evaluate. It's going to be square root a over 3 and a minus a over 3. So the value is going to be 2 over 3 So that is a local maximum value. My question is whether the function is always concave down, okay, if there are any inflection points. So you have to find the second derivative of the function. Okay, the second derivative of the function here is negative a over 4 x to the negative 1 minus negative 1/2 minus 1 3 over 2, and here minus 3 over 2 1/2 x to the negative 1/2, right? I think it's always negative. Clear? Because every term is negative. So it's always negative. So that means the graph is concave down. Okay? On the interval from 0 to infinity. Okay? So that's why no inflection points, and you sketch the graph. So this is the second type of functions. Right? The first type of function, polynomials, how to sketch graph of polynomials. Then how to sketch graph involve a square root of function, square root x. Okay. There are other type of functions. They are rational functions. Okay. Rational functions. You study the function y equals f of x, and here a typical example is x minus 1, x plus 2. Okay. And we can also put x, well, I can even put x minus 2, x plus 1. I already factored this out, but maybe I multiply this out to like x squared minus x minus 2. Here will be x squared plus x minus 2. So you cannot cancel it out. Okay. Yeah. Yeah, okay. So how do we schedule this graph? It's a polynomial. Well, at least you have to figure out the intercepts. Intercepts is when x equals 0, right? What is the y value? When x equals 0, y is going to be numerator is -2, denominator -2, so it's 1. Okay. Then you can also find out when y is 0, right? You get x accept. So x is going to be -1 and 2. So those are called x-intercept. All right, so the graph passes through those points. So let me draw the graph. And when x equals 0, y is 1. When x equals -1, y is 0. When x equals 2, right? So the graph passing through those 3 points. But we also should know that the asymptotes, vertical asymptotes. Vertical asymptotes when at the numbers where the function is not defined. So x is going to be 1, x equals -2. So -2 is here. So this is a line, and this is a 1. Okay, it's a 1 and a 2. Okay, the graph passing through those 3 points, but we also have 2 vertical lines. Horizontal asymptote, clearly y equals 1. Okay. So we don't know how to sketch a graph yet, but we know where it is, right? I can sketch the graph. I guess here's a graph. Okay, let me try. So the graph passing through those 3 points, and you have vertical asymptote. So I'm pretty sure it looks like that. Okay, it is a rational function. So another one must be here. So maybe it goes down like that. It's possible, passing through those 2 points. Okay, if it goes up, maybe you have another x-intercept, right? Then the other one must be here. Okay, yeah. So let's figure it out. So nearby x equals -2. I want to approximate the function, simplify the function. So the function here is x minus 1, x plus 2, x minus 2, x plus 1, right? So I only keep x plus 2. I only keep that term. So the rest of them I just evaluate. -2 minus 2, -2 plus 1, -2 minus 1, here x plus 2. Let me simplify. -4 times -1, +4. +4 divided by -3. So -4 over 3. Okay. So the graph of this simple function will be looks like that. Here's -2. The graph looks of this simple function will be like this. When x is greater than -2, it is negative. When x is less than -2, it's going to be positive. So this is how does the graph look like. So now it's this is a graph y equals -4 over 3 divided by x plus 2. Okay, this is the y-axis, this is the x-axis. So this graph is copied to here, and this 2 parts should be similar. Okay, when x is -2. So nearby x equals 1. So y is going to be almost equal to, you keep x minus 1, x plus 2, x minus 2, x plus 1 should be evaluated. So it's going to be 1 minus 2, 1 plus 1, x minus 1, 1 plus 2. Okay. So -1 times 2, -2 divided by 3 is going to be -2 over 3, x minus 1. Okay. How does the graph look like? This function? The graph of this function looks like 1, right? So it is when x greater than 1, it's going to be negative. When x is less than 1, it will be positive. Okay. When x equals 0, it's a positive number. So the graph looks like that. And then, and you can go up here. You see, yes, this is how does the graph look like, right? This portion. Okay. The other graph is that portion. Nearby the asymptote. All right. So I think the graph we draw here is already correct. Okay. So the question is, from here I can tell where the graph concave up, where graph concave down. Then there's 3 pieces, right? The one on the left is concave up. The one in the middle, somewhere concave down, somewhere concave up. The one on the right-hand side should be always concave down. Maybe concave down and concave up a little bit. Sometimes it looks like that. You know, it's possible. Still, it's possible if this is asymptote. It's possible going up, then approach that. Then in that case, this should be screwed, right? In this case, you know, this is asymptote, and it will go across the asymptote, then come down. Okay, then here there'll be inflection points. That's possible. Okay. So clearly from the above graph, at least I have 1 inflection point. 1 inflection. I haven't defined the derivative yet, right? I at least have one inflection point because this curve in the middle. One place concave down, other place concave up. As the concave changes. All right, so now we have a trouble to find the derivative. It's too complicated. Okay. So using the information we have, we already almost sketched the graph. So x squared. Let me copy the function minus x minus 2 plus x minus 2. Minus x minus 2 plus x minus 2. Okay. I'm going to find the first derivative. Okay. So that would be 2x minus 1 minus x squared minus x minus 2 and 2x plus 1. Whoa, we have to simplify. It's pretty complicated. Our first line is 2x cubed, 2x cubed plus 2x squared minus 4x, then minus x squared minus x plus 2. The second line, I have to put a negative sign, right? Then have a 2x cubed minus 2x squared minus 4x plus x squared minus x minus 2. Okay, let's see what we can get. 2x cubed is cancelled out. The first term is x squared, and negative x squared, so become 2x squared. Then I have a negative 5x minus negative 5x. It's gone. Negative 2 minus negative 2 is plus 4. So this is always positive. Always positive means the graph is always increasing. Let's go back to look at the picture. That the graph is, always increase. Yeah, going up, going up, going up, right? Every piece. So it's not a surprise. Okay. Then the second derivative should have zeros. Change the signs because somewhere concave up, somewhere concave down. At least look at this picture, right? Okay. So let's take a look at the second derivative. And times 2x plus 1. Wow, it's difficult, complicated, but at least you cancel one terms. You get 4x, x squared plus x minus 2, minus 2, 2x squared plus 4, and a 2x plus 1. So let's multiply this out. 4x cubed plus 4x squared minus 8x. I have 4 terms here. 2 times 2 times 2 is 8x cubed minus 16x minus 4x squared minus 8. And negative 4x cubed, 4x squared is gone. Negative 24x minus 8. I think if my computation is correct, it's harder to figure it out. Okay, take 4 out, you get x cubed plus 6x plus 2. Well, it is not a. It's almost impossible to find the zeros for the second derivative because you have to solve this equation. Polynomial degree 3. Right? It's polynomial degree 3. So I think we don't need to do that now. Okay. There's only one. Yeah, the denominator also changes signs. So the graph changes the concavity. What I want to do is, we almost sketch the graph. I want to make sure is whether this across the horizontal asymptote. If it does not cross the horizontal asymptote, then there's two pieces, one's on the left, the other one's on the right, is always concave up. But if it cross the horizontal asymptote, then have to go up again. Then the concavity changes. Okay, so to check whether the graph, besides the middle one, it approaches, it go across the, if it, check whether it goes across the horizontal asymptote. All I have to do is to see if this function minus equals 1, whether it has solution. Where's the solution, right? So it's x squared minus x minus 2, x squared plus x is minus 2. Yeah, I always keep forgetting this function. Minus, both are minus. And that is going to be 1. Then you get x squared minus x minus 2, get x squared plus x minus 2. X squared is gone, right? And negative 2 is gone, so x is going to be 0. So there's only 1 point, okay? There's 1 point, the value of function is going to be 1. So what is that point? This is a point, okay? So in other words, the other two pieces do not cross the, do not pass through the horizontal asymptote. So I think we are done with the problem. We don't need to find a second derivative, and we are not able to easily. Well, if you want to check the somewhere the inflection point is difficult to find out because you have to set this to be 0. Okay, this equation. Okay. So we are not going to find. Yeah, it's difficult to determine the inflection point. I should have said that. Yeah. So that's why the other two pieces do not intersect the horizontal asymptote. Okay, this is the only intersection point. Yeah, it's harder to determine the inflection point. Actually. All right, our next question. Yeah. What do you say?
The question I just saw. What is the final answer?
So final answer, you see, we want to sketch the graph. Our purpose is, okay? We want to point out where's the inflection point. But this problem originally is not asked for us to get complete information, just sketch graph. So I try, if my computation is correct, and I'm not able to even solve for that. You know, this is if I set this to be 0, I cannot get the second derivative. I cannot do yeah, this gives you the information, the inflection point. Second derivative 0, okay? But you see x cubed plus 6x plus 2, it's harder to find out. Okay, maybe -1, right? When x equals -1, no, it's positive 1. No. Okay, you can locate, you can find the interval where the root is, but probably don't get the integers. Okay, so I give up. But what I did here is it turns out to be to look at this equation, algebraic equation, and I find that the only solution is x equals 0. So then I look at the picture. This is the only solution. The graph at this point, the graph passes through the horizontal asymptote, and so the other two pieces that do not intersect the horizontal asymptote, okay, then it must be, one must be always concave up, other one must be always concave down, and this picture never shows up. Okay, this picture does not show up. Otherwise, you get another inflection point. You should only have one inflection point. We just want to sketch this graph. The main purpose is to sketch the graph. Get as much information as possible. Okay. Yes. Yeah. So we want to find out. Yeah. So we get to the intersection point. Yeah. Then we try to find the intersection point was a line y equals 1. Okay. So you set the f of x equals 1 then. The next problem is we have a cylinder, okay, but the top is open. Okay, we want to find out the volume is given. Volume is going to be just assume that 1,000 pi cubic feet, just for example, okay, and find this side is open, okay. Find the dimensions that will minimize the surface area. Does not include the top part. Yeah, bottom is included. Right. So find the dimension. Dimension means the height and the radius, right? So the volume is going to be pi r squared h equals 1,000 pi. And the surface area is going to be 2 pi r plus the surface area, sorry, not just pi r squared 2 pi r times h is the area of the side, and then area at the bottom is going to be pi r squared. Right? Okay, you want to minimize this area and find the dimension. So clearly, you should solve for h in terms of pi. So it's going to be 1,000 and r squared. Okay, so you get 2,000 r pi plus pi r squared. Okay, so this surface area has a minimum value. Okay. Because when r goes to 0 and or infinity, the area goes to infinity. So somewhere it has a minimum value. This is r, this is a. Looks like that, the graph. Okay, so then you set this to be 0. Then r cubed is going to be 1,000. Okay, r is going to be 10. Then h is going to be 1,000 divided by 10 squared. It's going to be also 10. So imagine you have to build. Yeah, if you want to build a cylinder, okay, like a plastic container cylinder type, right? And then without a cover, right? So what kind of dimension you can choose for the depends on size, depends how much volume you hold, right? If you assume it's 1,000 pi cubic feet, then you find out the height should be equal to radius. So my understanding is the cylinder must be look like that. This minimizes the material. Okay, the cost on that if you want to get. Okay, but our typical cylinder will be container will be like that plastic one you can buy from a supermarket. It looks like that, right? Right, and they have a hole, right? So that's not. It may be much easier to handle. That's not. That does cost a lot of plastic material for the same volume you can hold, right? And this is much harder to handle. Maybe you can put 2 bars on this side, right? That's possible. You see that this kind of thing, hold it. And like in the kitchen, maybe but not, yeah. So in reality, in reality, is maybe we're not going to make cylinder like this, okay? But we can do the computer. Yeah, the power of mathematics. I should say that, when sometimes you cannot, in reality, even cannot see it. Like dark matter, for example, it's actually proved using mathematics it exists, but you don't see it because it's dark matter. Okay, there are many things like that. You can use mathematics. So the existence proved by mathematics, okay, is really true or not? Truth or not? Okay, that's the question in philosophy. Okay. Yeah. Yeah, h is going to be see, h is going to be 1,000 over r squared from here. H is going to be 1,000 over r squared. So that r squared pi. Hold on. There's no pi here. Okay, pi is gone because I choose, I put the pi here for the volume. So make it easier. And then, yeah. Okay. Yeah, from the very beginning, it's gone. Pi is a very mystery number. It shows up as long as it's round, something like cylinder, circle. So pi always shows up. That's why. Okay. All right. Then we are going to study integrals. So we begin with the antiderivative. So if you have x square root x, right? X minus x squared, right? What is the antiderivative of this function? Right? Well, just find, evaluate the indefinite integral. So first of all, you have to express this as a power function, the sum of the power functions, which is going to be x to the 1/2 minus x 3/2. Okay. Then the antiderivative is going to be this. Okay, the most general antiderivative. It's going to be 2/3 x to the 3/2. It's going to be 2/5 x to the 5/2 plus constant. So problems like that is very simple. All right. Now this is a new problem. We haven't done that for a long time. X squared and this is no, not this x squared. I'm going to choose square root x 1 plus t squared dt. Okay, find the derivative of the function. Find the derivative function. We know that if integral here from a to u and g of any function, so I can put f here, f of t dt is going to be f of u. Okay, so this is what we know. Okay, the fundamental theorem calculus. Okay, we're going to use this to find the derivative. So g prime x is the derivative of this function, right? But you can also, you let u to be square root x. So that will be by the chain rule. And then du over dx. Okay. So this can be 1 plus u squared. And du over dx is of this. Okay. The du over dx is this. The derivative with respect to x. And then you replace u by square root x squared. then you get 2 square x, 1 plus x. Integral of x squared, x plus 2 dx. How about this? Yes. Yeah, please think about the last problem. Okay. To do this, use a substitution. Let u to be x plus 2. So du is dx, right? So the integral is square u and du. But how about x squared? You have to replace by u minus 2 square, right? And then you get u squared minus 4u plus 2 times square root u du. And then you have to multiply this out. 2 plus 1 half is 5 over 2 minus 4, 1 plus 1 half, 3 over 2. And this should be 4. Then the antiderivative of this function and plus constant. Okay. Oh, that's the u. All right. You can, if you don't want to put x back, you still have to say that we're using x plus 2. That's fine. Okay. But at least I have to indicate that. All right, I'm going to set up an integral for the region for the solid, okay, which is generated by located around the y-axis. Okay. So here's the equation. X equals square y. Okay. Okay, so this is the region. Okay, it's located about y-axis. Can you set up an integral for the volume? Set up 2 integrals. Okay, please do it. 2 integrals for this solid. Right. Then so we have 2 different ways to do, right? Use a horizontal knife to cut it. So you get cross sections is going to be disk, right? So this will be the height will be y variable. So the volume can be integral from 0 to 1 a of y dy. Okay, so you have to express the area's cross section. So this is a point x and y. Okay, I can write down quick, right? So this will be a circle. At that particular point, area just one disk, so r squared dy. So r is going to be x, but x is going to be square y, right? Yeah. Here, r is going to be x is square y. So that's the reason, right? You have this. So you end up with the same answer, integral pi y dy. So the answer is half of pi. But you can also use a cylinder to draw to sketch ground, right? To find the volume. So for the cylinder, right? This will be the radius r. So the volume is going to be integral r smallest value for I is 0, the largest possible value for I is 1, and AR dr. Okay, so AR is gonna be 2 pi r and multiplied by h. Okay, the only problem is how to express h in terms of r, right? So this is a point x and y. Then I know that I is going to be x, h is going to be 1 minus y. But x, y are related, right? X, y are related. When x equals square y, y is going to be square root x. So 1 minus square, x, y is x squared, not square. Hold on. X is going to be square root of y. Okay. Y is going to be, my drawing is not precise. Okay. So y is going to be x squared. Okay. So you can replace r by x. It's going to be pi. R is x, x is y. X is r, right? So it's x. And h is going to be 1 minus x squared and the dx. This does not look like equal to pi over 2, but after evaluate, it's pi over 2. Right? It's going to be pi over 2. So x minus x cubed dx. So the antiderivative is half of x squared, quarter of x to the 4th power. And after evaluate, it's 1/2 minus 1/4 is going to be pi over 2. Okay, so same answer. One more question about this type problems. So here's x equals y squared. Yes. Maybe.
Maybe, okay.
Right. So we have another function, x equals 6 y minus 2y squared. How does it look like? This looks like when x equals y0, x is 0, when because this is going to be 2, 3, 2y, 3 minus y, right? So it looks like that. So that's the intersection point here. So we are going to rotate it about this region, about the x-axis. Find the volume of the solid, okay? So the graph looks like that. I think it's easy to figure out the x for the same y value. Okay, so the best way to solve this problem is using cylindrical shells. Okay, yeah, I have to resketch the graph. Looks like that. Okay. So if we use a cylinder, very much easier to handle. Okay, the only problem is you needed to find the maximum value for the y variable, right? Okay. So the h and r. So r is going to be y, clear. But h is going to be the difference of these two x values. which one's on the right hand side? The parabola, so 6y minus 2y squared. Which one's on the left side? This parabola, okay? So y squared is going to be 6y minus 3y squared. This is h, okay? And the area will be AR. So the volume is going to be integral AR dr. But what is R? The smallest value for R is 0. The largest positive value R is the intersection point. Okay, intersection point. I have to find out the highest value for it. So we're going to have a, I don't know how many intersection points we're going to get. Okay, so we are going to get 6y minus 2y squared equals y squared. So I get 6y equals 3y squared. So y equals 0. Another y should be equal 2. So I think a 2 is the highest point. Okay, so it's 2. Then it's 2 pi r h dr. Now, if you use the r to be y value, then it's 2 pi y h 6y minus 3y squared and dy. Okay, because r is going to be y, so you can use y variable. So this is an integral for the solid, for the volume of the solid. Okay. The last problem is about, I did not do it in last review class, and that is going to be the, you lift the cable to the top of the building. Okay. So the cable is 100 feet long. Okay. And the density is going to be, no, total. We don't know the density. We just assume there's the whole cable. Yeah. The weight of the cable is going to be 20 pounds. Okay. It's 100 feet long, 20 pounds. Okay. How much work is required to lift the cable to the top of the building? I don't remember the formula for the integral because there's so many different type of problems there. I cannot memorize. I only remember the formula for the definition of the work: the distance it travels times the force. If the force changes, then you have trouble. You can, unless its force is constant. Okay. So the idea is you have to chop this cable into many pieces, and you look at each piece only. So if you draw the coordinate line, okay, this is called x, that's the starting point, and this is 100, right? And you cut them into many pieces. Okay. Okay, so delta x is going to be 100 over n, then xi is going to be 0 plus I delta x. Now, for the ice piece of the cable, yeah, that to lift the ice pieces of the cable, okay, defined by x greater than x minus 1 less than xi, okay? you needed to find how heavy it is, right? At that piece, this size piece, right? So the density is going to be 20 over 100. That's per how heavy per foot. And the length of that piece is delta x. So that gives you the weight of that piece. Okay? But the distance it travels is almost equal to xi. So you multiply xi. Okay? Then add them together. Okay. So the limit is going to be, as n approaches infinity, is going to be integral from 0 to 100, and delta x becomes dx, 20 over 100 x dx. That's it. So the antiderivative is going to be one. Yeah. Yeah. After you simplify, this is just the x over 5. So the antiderivative will be x squared over 10. So it's going to be 10 100 squared. It's going to be 1,000. Okay. Pounds, I think, pounds and feet. That's a unit. Okay. I want to see you show these details, not just give me the integrals. This is a requirement, even for the final exam. There'll be a problem like that. Okay. Total 18, no 17, 18 problems, including the bonus problems. And you have to draw the coordinate. You put a coordinate system there, and show us how to derive the formulas you can use to find the work. Then required to lift the cable to the top of the building. Okay. You can only memorize a few formulas. Don't memorize the specific integral for each particular problem.